and Dean of School of Basic and Applied Sciences, Professor Dr. Dipankar Bhattacharya, Head of the Department, Dr. Momita De, all senior professors, my colleagues, and dear students. Welcome to the distinguished lecture series in physics. So, Department of Physics has been organizing this lecture since July 2021. This is the first lecture of the series in 2023. So, today distinguished lecture is also a tribute to the National Science Day, which is celebrated in India on every 28th February to mark the discovery of the Raman effect by Indian physicist Sir C.V. Raman on 28th February 1928. So this year, unfortunately, we could not celebrate it on that day because of some overlapping events. However, it's better late than never. So we are here celebrating National Science Day with a lecture from a distinguished physicist, Professor Archon Majumdar, Senior Professor of S.N. Bose National Center for Basic Sciences, Kolkata. He will enlighten us about the quantum information and foundations from basic science to technology. So I would like to take this opportunity to call upon stage Professor Dipankar Bhattacharya to say a few words and felicitate our speaker.
Good afternoon, my dear students and all my colleagues present here, and especially I thank Professor Archon S. Majumdar for his time, and we will learn a lot from him actually. And this is really some kind of effort that I must appreciate from Department of Physics. So I thank the head of the department, Professor Momita De, and her team. It's really nice to have it here. So without much ado, I will start with the introduction of Professor Majumdar. Dr. Archon S. Majumdar did his PhD in theoretical physics from the Department of Physics and Astrophysics, University of Delhi in 1994. His research interests lie in the fields of gravitation and cosmology, as well as in quantum foundations and information theory. He has authored more than 150 research papers and review articles in these areas, and also delivered more than 50 invited lectures in various conferences, academic and research institutions, and laboratories all around the world. On topics such as inflationary cosmology, I don't really know. I know about inflation, but probably it's the expanding cosmos or something it should be related to. Dark energy, primordial black holes, quantum teleportation, measurement problems in quantum mechanics, and environment-induced decoherence. Going like this. Okay. He has supervised the research of 15 PhDs in the above areas. Currently, he is involved in the Quantum-Enabled Science and Technology program of the Department of Science and Technology, Government of India. Professor Majumdar actively participates in science society interface programs and workshops. At present, he is a senior professor at S.N. Bose National Center for Basic Sciences, Kolkata. I was just discussing with him when he was talking about this quantum-enabled science and technology. I only know few things it's about quantum computing, but he mentioned there are 4 verticals to it also. I learned those things, but this is really some modern research areas. So you should learn what he delivers. So it's a really interesting topic, and it's a cutting edge one also. Thank you, sir. So the stage is all yours.
So I would request sir to come up to the stage. I would also request Professor Bimal Kumar Sarkar, Senior Professor of our department, to come up and join in this tip. And also Professor Aparajita Bhattacharya and Professor P.K. Datta.
Yeah, please. So let me begin by thanking the organizers, Professor Bhattacharya, the Dean, and Professor Sarkar, and everybody else who I'm not naming individually, but thank you so much for this invitation. And I'm really happy to come here to this campus. Is there a pointer? Yeah, this is fine. Is there a pointer? Is there a pointer? Anyway, let me just begin today's lecture. So it's a wonderful experience for me. I have heard about this Adamus University, and I'm really glad to come here. This is my first visit, and I'm happy to note a lot of interested faculty members as well as students here. And I hope that you will take the lead in carrying the academics to a very high level in the coming days and years. Okay, so the topic of today's lecture is quantum information and foundations, and the sub-theme is from basic science to technology. And as all of you have heard, that I work at the S.N. Bose National Center for Basic Sciences, Kolkata, in Salt Lake. So now this area is somewhat new. It does not form a part of the traditional physics. Of course, I wonder, I mean, most of the audience here, they are you physics undergraduates? Undergraduates and postgraduates. Okay. So at least you have come across quantum mechanics in some of your courses, and basically you have learned the history of quantum mechanics. So when quantum mechanics was first formulated in the early part of the last century, there were some questions which the founding forefathers raised. They could not understand the basic notions of this subject, the sort of weird, quote unquote weird or counterintuitive features of quantum mechanics, and that became a topic that became to be called the topic of foundations of quantum mechanics. And this topic of foundations of quantum mechanics was there, but it was relegated to a corner of the mainstream syllabus because not many active physicists bothered about this at that time about this. Why? The answer is clear. Because in the last century, those of you who have studied the history of development of physics and basic physics know that so many wonderful things happened. Okay, so on one direction you had relativity applied to quantum theory. You had field theory, particle physics, very successful discovery of particles. On the other side, you had the cosmos, general relativity, cosmology, many different kinds. Then you had applications like lasers, etc. So people, I mean, there was so much excitement, people did not bother to think about it for a long time. However, there were some die-hard physicists who still bothered about it, and notably among them was, I should take the name of John Bell, who in 1965 wrote a seminal paper, and that was a landmark work after the original work by Einstein and collaborators. But still, I would say till the 1980s or 90s, there was not much interest in the mainstream community. However, starting from 1990s, two major developments happened. First of all, is it clear? Yeah, I hope I am audible, because anyway I speak loud, so if you can't hear, I can even speak louder. So first of all, in the 1990s, there were some information scientists or computer scientists who started bothering about applications of information theory in quantum mechanics. So that ushered in a new field of quantum information. And secondly, due to the advancement of technology, people were able to do experiments using single atoms, single molecules, single electrons, and single photons. So that is extremely important for the development of this subject. So starting 1990s onwards, there was a huge revolution in this subject, and now after about 20-25 years, we are at a certain stage that this cannot be ignored whatsoever, because this has brought in prospects of tremendous new technologies, as I will come to very soon. And also this has many practical ramifications. For example, this is directly related to security. And security of what? You can ask. Primarily at a very basic small level, even such things like security of, say, communication, security of financial transaction, etc. These days all of you know how many, I mean, bank scams happen. For example, you are communicating something using your mobile phone and somebody else is withdrawing your money. So what provides foolproof security? It can only be quantum mechanics through fundamental laws of physics. So that is why this subject has become extremely popular and important. So what I will be talking of today, I will give you a basic introduction to this subject, and I would also try to, highlight it, because I also thought that maybe in the audience, because this is a university, there may be some students from other areas also, for example, chemistry, biology, etc. But don't worry about it. Even those of you who are physicists should learn that this has become a very interdisciplinary area with prospects of applications and input from many different branches of science. And this basically, what is quantum information science? So quantum information science aims to have a fundamental understanding of nature, okay, of the nature of the physical world through information theoretic principles. So this is a merger or amalgamation of information theoretic principles into the physical world. And as I said, I want to emphasize again and again, there are plenty of applications. For example, one of the streams is, all of you have heard of quantum computers, that is one. But quantum computers may take some time to be actually achieved in practice. But what is already put in practice is the area of quantum communication, okay, or quantum cryptography, quantum secret sharing, things like that. So I will like to emphasize this, and I would like to point out how secure information sharing can happen using laws of quantum physics and quantum information. And secondly, you're already aware of quantum computing is a big area, and though we do not have real quantum computers so much today, but still we can simulate the action of quantum computers, and we have come across examples, all of you know, like Google, etc., who are doing a wonderful job, and even doing that, they have come across applications in many different areas, not only in physics, but as I was emphasizing, simulation of complex chemical and biological processes as well. Okay, so does this slide in your work? Fine, fantastic. Okay, so now let me thank you. Let me come to the start of the formal talk. And so as I was saying that those of you who have learned quantum mechanics or in the process of learning know already that this is one of the most important founding pillars of modern physics. And this was developed starting from the early 1900s due to the seminal work of many distinguished physicists like Niels Bohr, Max Planck, Albert Einstein, Schrödinger, Heisenberg, Dirac, so on and so forth. And what were the key elements in quantum theory which actually went beyond our well-known classical notions of physics? And there were at least two of them, and these are called the uncertainty principle. Of course, in classical mechanics there is no uncertainty principle, and the other idea of superposition of basic quanta. That is also very important. So this in a way is slightly goes beyond the concept of superposition of classical waves that all of us are aware of, or people were aware of even before the development of quantum theory. So these two principles, superposition and uncertainty principle, were the key hallmarks of the recently at that time developed quantum mechanics in the 1990s. So people said that this brought about the first quantum revolution, because starting from it our whole concept of the physical world changed, and not only that, it brought about completely new technologies. For example, it brought about lasers, it brought about transistors, and in the application world of the 19th century could not be complete without using things like lasers and transistors. All of you are aware. So that is history. But what happened later on, as I briefly alluded to in the first part just a couple of minutes ago, so certain key developments happened starting from 1990s, and this was indeed motivated by some foundational issues of quantum physics. So which was there in, say, one chapter of textbook, and which nobody bothered about for many years, 50, 60, 70 years. But again, a relook of that, and in combination with information theoretic principles, has brought about a second quantum revolution, and this has tremendous potential for new quantum technology. So that is very important. So let us just briefly go about and try to understand what has happened in the whole development of physics, which has changed our outlook in the last 200 to 300 years. So how, first of all, how did we go from classical to quantum physics? Okay. So as many of you may be aware in the 17th century, Newton, who after all, I mean everybody knows about Newton, and his main contributions are too many actually. So starting from Newton's Principia, okay, he developed the mechanism of calculus, to Newton's laws of motion, Newton's laws of gravitation, so on and so forth. So if there was no Newton, one wonders what would have happened of physics. But after he actually came up with his laws of motion and gravitation, as well as developing calculus, he started wondering about the properties of light, because light is something which is ubiquitous. Everybody has to live in light. I mean, nobody can live in darkness. So he's shone light at a prism, and he saw that on the other side the colors were separating, and then Newton tried to understand it. So he came up with an idea that light consists of particles, and each particle has a certain color which is evident from the spectrum. So this was Newton way back in the 17th century. But then 1 century later came again these famous people, that is Thomas Young primarily, and he performed this double slit experiment using light waves. So light waves are coming from a pinhole and they are falling on two slits, and here you see an interference pattern. So this actually again completely overhauled the worldview of light. That is, now after this experiment by Young, it was generally accepted that light was made of waves rather than particles. Because how can particles interfere? Because people at that time knew about sound waves, water waves, etc., and those actually interfered. And similarly, if light could interfere, it must be a wave. So they came up with this wave theory of light. But again we move, and we are jumping in say about approximately 100 years. So then in 1905 came Albert Einstein, and what he discovered famously was for this photoelectric effect. And all students should actually know this. I mean, I think most of you know it. Einstein is extremely famous for his laws of relativity, but he got his Nobel Prize not for the laws of relativity but for this photoelectric effect. Okay. So what Einstein actually showed was the following, that if you have a metal and if you shine light on the metal, and then if you vary the intensity of light, nothing changes. But if you actually change the frequency of light from say the red to the blue spectrum, blue side, then you have more and more emission of electrons. So that is called the photoelectric effect. And now this fact that the emission actually depends on the frequency rather than the amplitude, rather than the intensity, cannot be explained by the wave nature of light. So again we come back to the corpuscular nature. So by this time people wondered that light is already well known as a wave phenomena, but here you see that it is again exhibiting a particle-like behavior. Okay. So then physicists after that came up with this idea of wave-particle duality. That is, and what is this wave-particle duality? That fundamental quanta, fundamental elementary particles can behave both as particles as well as waves, but never, these two things can never occur together simultaneously in the same experiment, and that is actually paraphrased by this principle of complementarity, which tells us that a system can exhibit wave-like behavior as well as particle-like behavior, but no single experiment can demonstrate both behaviors simultaneously. So again this brings about the sort of a weird or strange nature of elementary quanta, elementary particles, and this is true for not only light, but it is also true for massive particles like an electron, okay, or a neutron. And therefore when an electron or a neutron starts behaving like a wave, then of course it has to have a characteristic wavelength, and that is given in inverse of its momentum, okay, and h is the famous Planck's constant. So for example, if you note down Planck's constant, the value is extremely small, and if a standard particle, even a small mass particle, has any particular small velocity or momentum, you see that this wavelength turns out to be extremely small. So this is beyond the reach of normal experiments. So that is why characteristically you do not observe wave nature of matter, but you can indeed observe them if you make those type of conditions. Okay. So then science progressed. So for example, if you have a wave nature of elementary particles, then a single particle can also superpose with itself or interfere with it. Okay. So this is the famous experiment which shows us that a single particle can interfere with itself. Okay. So for example, If you take a stream of electrons and you pass it through two slits, of course you will observe some interference pattern. But if you take a single electron, okay, and there are two possible slits through which, or two possible holes through which it can pass, then if you have a screen on the other side, wherever it hits, it produces a mark on the screen. Okay. However, if you repeat it with thousands of electrons, but you arrange it in such a manner that any given instance only one electron will pass through either of these two slits, then at the end of your experiment you will again observe an interference. So what is happening? That as if a single electron is behaving like a wave, such that their probability is non-vanishing through either or both of these slits. So that is how that is why such interference can be produced. Okay, so that is what people saw to their surprise, that the interference patterns were still produced even if you have single electrons passing at a time. Okay, so that is the fact. It meant that a single electron was passing through both slits and interfering with itself. But how can a single electron pass through both slits? It cannot if it is a particle-like object, but it can if it is a wave-like object. So whatever is happening with photons is also happening with electrons. Okay. So now what happens is that, so this weird feature of matter interference is also exemplified again in this slit. So suppose again this is a summary of what I said in the last several slides. So there is a screen with two holes or two slits, and you have a stream of electrons which pass here, and on the right side you have an optical screen. So what is an optical screen? Basically you can regard it as a collection of detectors. Okay. So wherever a single electron strikes, you observe a patch on the screen. So now you take thousands of electrons and they wait for the experiment to get over, but one electron is passing any of these holes at a given instant. But after the experiment is over, you see a definite amalgamation, clustering of electrons at certain spots and emptiness at the other spots. So what does it indicate? It indicates that this electron is indeed obeying a wave property. Okay. So right hand side is just a collection. And by the way, if you close one of these holes, for example, if you actually close this the hole at the bottom, that is this blue one, then what you observe? Then you observe all electrons will pass through only one slit. Okay. And then you observe this red line. Okay. So red line is also showing a modulation, and those of you who studied, this is nothing but the dispersion, okay, pattern, diffraction pattern from passing of an electron through a single hole. Similarly, if you close the upper hole, you observe this blue line. But if you let the both holes open, then what you observe is this pattern. Okay, so this is interference overall, again with some diffraction. So that is the famous character of a single electron, and because it can pass through both slits at any single instance, then it can be labeled by two entities. For example, if we say that if it passes to the bottom slit, I label it by 0. If it passes to the upper slit, I label it by 1. Then it has two entities. And now because it can superpose, I can make some combinations like 0 plus 1, 0 minus 1, and not only that, I can put some weights, okay, say A0 plus B1, so on and so forth. Then you can see that infinite number of possibilities are there. Okay, so this electron, and as it is by now, those of you who are have learned some basic elements of, say, Boolean algebra or computer science, know that we are already talking in terms of bits, but some strange bits, because if you regard these two as bits, then what are these? These are a combination of bits, superposition, so we come to 2 bits. So I will come to that in a moment. And so this is an interesting aside. So people wondered after this experiment that suppose how does the electron know whether it has to pass through this slit or that. So suppose the electron already passes, and then later on somebody inserts the detector. So will the electron start behaving as a wave or a particle? So this is called the famous Diglett choice experiment, which was proposed by John Wheeler many years ago, 60, 70 years ago. But without going into the details, if somebody is interested, I can talk about it later. So this Diglett choice teaches us that no matter what you do, so you can insert your, say, output beam splitter, even after the single photon or electron has passed, has entered the apparatus, but still you cannot dictate whether the electron will pass to the upper arm or the lower arm. So this is some fundamental property of nature which is governed by the context. Okay. So now let us come to the main focus of this talk. So as I said that a classical bit can take two of these mutually exclusive values, 1 or 0, but because now we are within the world of quantum mechanics, so every bit, every single entity can interfere and superpose. So therefore a quantum bit or qubit can take any possible superposition of bits. So if you take this sphere, a spherical surface, and label the north pole as the 0 bit and the south pole as the 1 bit, then you can see there are infinitely many possible combinations, and for example this direction, whichever direction you like on the surface, it is labeled by the 0 plus 1 normalized by this. So this is the power of a qubit. Okay. So therefore we come to this aspect. So what was the key features which actually led to this second quantum revolution starting from the 1990s? So before we go into that, let us just bother for a moment and try to think. So I told you information theory made an impact. So basically what is information? So if you come to think of information, information can be stored anywhere, and this slide, by the way, is slightly an old-fashioned slide. So it may appeal to some, older faculty members here, but it may not appeal to the newer students, because many of the students these days do not know what an encyclopedia is, because many of them have not gone to a library, and you also don't need to, because you can sit on your laptop and computer and mobile and you can find anything. But even if you go to some old library, you will see that there are objects like encyclopedias there, okay, and these contain a lot of information about any particular subject that you like. So then basically, so this is the information which is stored in an encyclopedia. But then if you try to think a little bit deeper, that encyclopedia, what you open the page and you think that something is typed. Okay, so what is typing? It is typed in some press, and in the press there was basically some ink. So after all, what is the ink composed of? It is composed of some molecules. So essentially what information you are gathering, it is actually encoded in the state of a physical system, in this case on paper using ink. So you cannot think of information beyond the physical system. Okay, so it has to be encoded in some system which the properties of which you can study by using laws of physics. Okay, so now because we know that all physical systems, if you come down to the level of molecules and atoms, they are governed not by classical physics but by laws of quantum physics. So essentially then information is encoded in the state of a quantum. So this is very important. If you want to study information theory deeply, you have to worry about properties of a quantum system. So this is how quantum mechanics come naturally into information science and vice versa. So now let us look into the properties of bits. So to begin with, take a classical bit, okay, and all of you know that a classical bit can be labeled by two entities, 0 or 1, which pictorially let me convey by a red ball and a green ball. So now let us say that you prepare these two bits and then you want to store them. Okay, you want to store them, and for storing them you have a particular black box which has two doors, one on the upper side and one on the front, labeled by 1 and 2. So suppose you actually prepare a red bit, 0 bit, and push it down to door 1, and similarly a 1 bit you push it down to door 1. And after some time you let it remain like this, but later on somebody else comes and tries to open this box. Okay, so then what happens? So if you open this box, for example, if you open this first box, which you know that you had pushed a 0 bit or red bit inside, and then what you find out is again that the red bit comes out. Similarly with this one. So what went in comes out. So this is very trivial. Even a 4-year-old child will tell you that if I have put in a red ball inside a black box, if I open the door at some time, I will get a red ball, unless somebody is doing some magic. Okay, so this is completely familiar. So now let us regard that instead of a bit, you are actually putting down a qubit or a quantum bit. And qubit, as you know, because then you have to actually specify that the thing that I wrote down here in the earlier slide, that is 0 plus 1 by root 2. Okay. So immediately those of you who have learned quantum mechanics or learning will ask me, but I have to specify something more. I have to specify what is my coordinate axis, because these are nothing but eigenvalues of the spin vector. So which side is my spin aligned? So is it sigma x or sigma y? Okay. So therefore you have at least two ways of preparing such a bit. And now, for example, you prepared this big bit along the sigma x direction. Again a red bit which I label by 0 of x, and you push it in from the first door. And on the other hand, you also prepare a 0 z along the z direction, and you push it in along the second door. So those of you are thinking a little bit can immediately say, why are these two doors relevant? Because these two doors are two different ways to either prepare or measure the quantum system, which has to be with respect to a certain direction. So now what happens? Okay. So now you will again do the same thing, let it remain there, and then you take the door out. But now what do you see? So suppose you open the same door that you closed while preparing the system, you can recover the bit from the box, exactly this door and this door. Whatever you sent in came out. That is, in quantum mechanics, what is happening is that you define an eigenbasis, and there is an eigenstate. You make a measurement on the eigenstate, you get back the same eigenstate, right? But now suppose pictorially you do repeat the same experiment, but while measuring you actually open a different. Okay, so then what happens that 50% of the time you will find the red ball, and 50% of the time you will find the green. So green or red are only ways of pictorially representing it, but the essential physics is that if you make a measurement along a different direction than the direction you chose to prepare the state of the system, then naturally your outcome will change. Okay. So this is a fundamental property of quantum measurement, and this may seem to be very trivial, but this has extremely profound consequences. And one of the main consequences is the following, that you cannot have a quantum copier. Okay, so again, copiers you are familiar with. All of students use Xerox machines since their childhood, but you can never have a perfect quantum copier. That is the consequence of this, whatever I told you. So you cannot clone perfectly any unknown quantum state. Okay, so don't take this sheet too seriously, because after all this is a classical thing. But even then, even a classical object can have quantum states. You can never replicate an unknown quantum state, be it small or large, perfectly. Okay, so the laws of quantum mechanics prohibit us to do the same. So now you can ask me, what are the physical manifestations of this qubit? So the most common one is photon polarization. So those of you who have at least learned a little bit of optics know that a given photon comes in two polarizations, horizontal or vertical, and you can regard them as the two orthogonal states of the qubit, that is 0 and 1. And of course now if you have this, and then using a superposition, you can construct infinitely many possible qubits using photon polarization. So that is why, because photons are so ubiquitous, available so easily, most of the information processing that is done today, mainly in the area of quantum communication, is done with photons. Okay, so that is one thing. As I said, that quantum superposition or quantum measurement is one of the key elements which actually has connected us with quantum information theory. But what is the other, and I would say the most important element of quantum information, and that is called quantum entanglement. So this has actually no parallel in classical mechanics. So this is what is called quantum entanglement. And by the way, what is quantum entanglement? Okay. So this is a magical thing. So these days you open up anything, you give a search on your mobile, and you just type the word quantum entanglement. You will come across millions and millions of articles, ranging from scientific articles to popular articles, stories, science fiction, so on and so forth. So this idea has moved the world so much, at least in the last 20-30 years, but still it has an interesting history. So as again to repeat that quantum mechanics is one of the most successful scientific theories, and it is essentially the theory of elementary particles, and the knowledge of a particle elementary system that you have is encoded in something which is called the wave function or Schrodinger wave function psi. But now let us say that instead of a single system, you have a composite system. So collection of say 2 photons, 2 electrons, or 10 atoms, 10 to 20 neutrons, so on and so on. So something which goes beyond one. Okay, these are called composite systems. So again, your physical properties are described in terms of the wave function, and in quantum mechanics, you know that the dynamics is given by the Schrodinger. But if you have two entities, okay, A and B, then you can again do the same thing. You can solve the Schrodinger equation and you can obtain the joint physical state. So this joint physical state will be labeled by two things A and B because we started with two entities to begin with. Now, what is an entangled state? It is extremely simple. So whenever you cannot write this joint wave function as a direct product of these two individual wave functions, psi A tensor psi B, then you have an entangled state. Okay, so this is extremely simple. So you can take a collection of 2 or n or whatever objects. Whenever you cannot write it as a direct tensor product of this of the two individual entities, this is called an entangled state or an entangled state. But behind this definition lies an extremely deep, physical meaning or sense, and in one line I can summarize it as follows. So whenever you have an entangled state, then you just cannot make an individual description of either subsystem A or subsystem B. In other words, if you have an entangled state and still you want to make sense of individual subsystems physically, you will completely fail and you will obtain weird, extremely weird answers. Okay. So in this case, one can only talk of joint properties of the total subsystem. And we will come to this weirdness soon, but again to give you another physical sort of illustration of it. So as I said, if your psi AB cannot be written as a tensor product of the individual wave functions, then you can have an entangled state. And physically, how do such things arise? Suppose you have a source which emits two particles. So then normally these two particles will be entangled if they come out of a common source. And very common examples are two spin-off particles which can be emitted from a common source. And again, all of you who work in many different branches of physics, for example, solid state physics or whichever branch of physics, are aware of these spin states which are called singlet states, triplet states, so on and so forth. So this is one of them is the singlet state and the other is the triplet state. So you have, in this case, you have these two spins perfectly correlated. Okay, so that is the meaning of entangled state. So suppose you take this psi minus state, so that will tell you psi z up, psi z down, minus z down, z up. So one of these entities, if you measure spin down, the other will automatically be spin up. Okay, because the total angular momentum is constant. So these states are also example of maximally entangled states, and these are used as fundamental resources in quantum information processing. Okay, so to again summarize, so suppose these states in quantum mechanics are mathematically represented as rays in the Hilbert states, which are labeled by K tensor G, and the state of a composite system can be taken as something which can be written as a direct product if they are not entangled, but generally it is defined in terms of these coefficients, which has elements of both the bases, I from A and J from B. So an example from two basis vectors I have already given you. So this can be spin of 2 electrons or polarization of 2 photons. And what is the meaning of entanglement? Okay, so the meaning of entanglement physically is nothing else but the ability of two or more particles, I should say, to first of all acquire some correlations, okay, because you see the spins are correlated as I just told you, and not only acquire but retain for a certain duration of time correlations in what? Correlations in their physical properties. Okay, so for example, we were talking about spin in that case, but it can be also polarization, and even when they move far away from each other. So that is extremely important for practical applications. So if you have a source of two photons and they are correlated or entangled, and if they move away far away from each other and still actually retain this correlation, we can use this entanglement for doing many wonderful, surprising, wonderful, fantastic work. Okay, that I will come to. So these are useful as a resource to perform various physical tasks. So historically, actually, this feature is again very old. So it is almost now 90 years old. It was first noticed by the famous work of Einstein and his two students, Podolsky and Rosen, in 1935. And immediately following this, Schrodinger wrote a paper in 1935 and 36. So from their work came out this idea of entanglement. Schrodinger actually defined this word entanglement, so which is completely absent in particle physics. And by the way, this is the famous EPR paper, and till date I think it ranks as one of the most cited or viewed papers in all of physics, okay, at least all of basic physics. So let us not, it has a deep philosophical meaning, but let us not go into those aspects. If anybody is interested, I can tell you. But I will just highlight what Schrodinger wrote in response to this EPR paper. And that is, if you understand this, what I have circled in red, that means you at least understood half of the meaning of entangle. So what does entangle tells us? That if you have a composite system, then the best possible knowledge of the whole does not necessarily include the best possible knowledge of the parts. Okay, so that is the most important thing, the most important message of quantum physics or quantum entanglement. Okay, so that is something which is extremely important in this context. Okay, but Einstein regarded this as something very strange and funny, because you see, when the particles have moved far away from each other, then because Einstein actually himself discovered relativity, he knew that if two entities are very far away from each other, physically anything happening on this side cannot influence one on the other. So to him, so this was a relation of something non-local. That is, how can properties of two systems be tied even if they are far away from each other? And in principle, there is nothing to stop, because if you have an entangled pair, one of the particles is on Earth, another is on the Moon, and if there is no decoherence, entanglement will be still preserved. And by the way, so far the experimental situation is such that although we have not been able to do any such experiment at the level of the Earth and the Moon, but still quantum teleportation has been performed successfully from a satellite which is orbiting the Earth to the Earth. So it means that people have successfully not only created but maintained or retained entanglement between two particles, one of which is on the Earth, the other is on a satellite which is orbiting the Earth. Okay, so it has been experimentally verified. But then Einstein thought it was something very strange or something non-local or spooky action at a distance, which is by the way the meaning of this word in German, which Einstein explained, that it is spooky action at a distance. However, I should also clarify before we go into the main slide. So the current understanding is that there is no as such spooky action at a distance. Nothing is traveling faster than light. But when the particles which you have created at some point which were together, they have some correlation. They may move far away, but these correlations in their properties are retained, and they can be revealed by performing suitable methods. Okay, nothing is traveling faster than light, so there is no violation of laws of relativity. So by non-local we mean non-local correlation, right? Okay. So then one of the famous examples is, I said, teleportation, that I was just talking about. So this is no longer science fiction. So when we were students, that is many years ago, 30 years ago, there was this famous TV series which actually is a Captain whatever, and then it was a science fiction. People saw that some strange astronaut appeared in one galaxy and appeared in another galaxy. So that the name teleportation, by the way, was coined after that, and nowadays this is reality. Of course, not at the level of human beings so far, not even at the level of cats and dogs, but at the level of single particles or a collection of small particles. So exactly teleportation is that. So if you have an original object, okay, and the original object is with some party which is here, and you have an entangled pair. See, this is very important, an entangled state which is shared by this party as well as another, a friend of A who is very far away. Then by using some measurements and of course sending some classical communication, you can create an exact replica of this original object at a faraway location. So that is what is called quantum teleportation, and the original object of course will get destroyed in the process, otherwise you will violate something which you just learned, that is the quantum no cloning principle. But such a thing can happen, and physically this object is not functional. Okay. So that is most important thing to realize, and this has indeed happened on the many experiments on the surface of the earth, and one experiment at least connecting the earth to a satellite. Okay. So we need not go into the details of teleportation, but this is one of the most curious and wonderful things. So if you tell this to a young fellow, or I mean somebody, even a school kid, he or she will be very fascinated by it. So those of you who are interested can try to learn and look into this, what is quantum teleportation. But this is something magical which can never happen using the standard laws of classical physics and standard principles of classical communication theory. So this is a central application of quantum information. Okay, so this is more to do with teleportation. So let me just skip it, and let me come now to something else, that how do you accomplish. So the teleportation is very important, and it is also very useful, and let me just spend some 10-20 seconds in telling you why it is practically relevant. So many of you have heard of this word of quantum computation, but at least those of you who have not, at least you know of classical computation. So classical computers, we have very large machines and very nice, very good machines also, but there is always a limitation, how much you can do. Okay, it also depends on the algorithm you are running and the amount of data you are using. So the idea is, suppose that you do not depend on one computer, but you have say a number of computers, and these are connected by a network, right? So then each computer, exactly what happens in parallel computing in a way. So you have different computers at different locations. Now if you are able to connect up these computers, then the problem of building one large computer at a single place goes away. Okay, so this is very roughly speaking what I am saying. Now when you want to do quantum computing, if you can connect it just like you are familiar these days by cables or something, then you can't do much. You have to apply laws of quantum information, and you can only do that using teleportation. So that is why this is a most important object, the most important area of teleportation. And since teleportation is important, so then it becomes important to demonstrate teleportation. Now if you want to demonstrate or achieve teleportation in your individual laboratory, what is the first question that you will ask? Of course, this is I made a few lines of advertisement. So not only teleportation, there are other things like cryptography, error correction, etc., which you can do. Now the point here is that you need to create entanglement in the laboratory, but even if you create entanglement, somebody has to demonstrate. That is, there is indeed entanglement, as I just showed you. So how do you detect entanglement in the laboratory? So that is one of the most important questions, and you can rephrase it in another way. So suppose somebody has prepared a state of say elementary particles, electrons, photons, or whatever. So and he or she has prepared and given it to you. Now you want to use it for some fantastic applications like teleportation or key generation or whatever. Will you be successful in doing that? So that is the most important question. So suppose there is an unknown state, because after all, what is a quantum state? Something that you write on paper, mathematics. But suppose somebody has given you two particles. Do you know its quantum state? No. So then suppose somebody has given you a state of two or more particles. Can you tell whether it is useful for information processing or not? So how do we go about this task? The methodology again comes from beautiful quantum mechanics. We actually construct some operators, and those of you who learned quantum mechanics know that all operators which are measurable or have real expectation values are Hermitian operators. So you construct something which are called witness operators. So what do these operators do? If you apply them on the unknown quantum state, they can witness quantum entanglement for you. So if you measure the expectation value of such a witness operator on an unknown state, it will tell you whether this is entangled or not. So this is again a well-known idea in quantum information. And then of course you can do another technique also. You can do something like measure the state directly, which is called state tomography, but you have to compare which is more expensive, okay, in terms of research. So now just to give you a flavor of what kind of research is happening in our group, for example, in the SNBO Center. This is by the way old, now more than 12 years old. So we were the first to suggest that such witness operators exist for not only quantum entanglement but for quantum teleportation also. So this was our contribution, which appeared in Cryptography letters many years ago, I mean 12 years ago. And this has been very recently again practically applied by a Korean group in this process which is called boson sampling. That is a completely different idea. But boson sampling makes use of the protocol of entanglement witnesses for quantum teleportation that we propose. So that is a very brief aside in trying to show you what kind of research is happening. Okay. So now quickly towards the end, I move to some more, fascinating areas which have come about as applications of the subject of quantum computing. And quantum computing is very natural. It has to happen. If you just pay a little attention on this slide and the next slide, you know that what is happening in terms of actual computation, classical computation. So as we move on in terms of years, by the way, this slide is also 15 years or more than 17 years outdated. So now you can imagine what is happening. So the technologists are developing more and more, more sophisticated processors. And you can see here that the number of transistors, basic fundamental transistors that we learn in solid state physics, that is there in a single processor, the number was as small or as big as 4,000 in 1970, and even at that time it was regarded as a big number. So for example, again for students, you should know that in Kolkata in ISI, P.C. Mahalanobis was the first who got these computers, and still today you can go and have a look at those computers. So they took a huge room to keep. They were very, very, very big computers. Okay, but still at that time the technology was such that you had number of transistors on a single chip. But now, if you come into, for example, look the most modern, not the most modern, but the 15-year-old versions of these Intel processors, then you count this, how many of this is 100 billion transistors. Okay, so that means if you come to the next slide, and if you actually look into this, if you compare the size of such a chip, by the way, this is an ant is holding a chip in its beak. Okay, so ant all of you know this is the size of the chip, and this has 100 million transistors. Okay, so just imagine the smallness of this object in nanoscale or whatever. So then you see that so many transistors are packed together on a single chip. So now, how will this chip behave? Will it behave, according to classical laws of physics or quantum laws of physics? You tell me. Of course, quantum laws of physics. And not only that, because transistors are anyway quantum. Somebody can tell that these transistors were discovered much before quantum information. But the way you handle information flowing from one transistor to the other, that is, you store and process information, it cannot be governed using classical laws of physics. That is the most important point. So you have to apply laws of quantum information for computers. Okay, so quantum computing will come naturally. There is no sort of way to evade it. Okay, and so because now again, as I said, that some people may think that it is only a thing for physicists and computer scientists to bother about. The answer is completely not. By the way, you also have many friends in other departments. If you see them, you tell them that you will have to also use quantum computers. There is no way out. So many different processes in chemistry, biology, space, time, so on and so forth. I'll just give you one or two examples. For example, in chemistry, sometimes it is very important to obtain the potential surface energy, and for that of say a nuclear, you have to solve the nuclear Schrodinger equation. And if you use a classical, say, computing method, then it will take you years to obtain a very basic. But a quantum algorithm using, say, the Google supercomputer can do it in some minutes. So this is one example. There are many other examples, polyatomic surfaces, I don't need to go into it. Even in biochemistry, the way one devises drugs, does simulations in the laboratory to devise many, many different drugs. So this has to depend on quantum algorithm, because the power required for a classical computer it is becoming fantastically large. No classical computer will be able to achieve such power. Okay, so now I move to, in the last part of my talk, I move to something interesting. So people can say that science is very boring, because science happened, most of the basic science happened, say 100 years ago or 50 years ago. At least some quantum science is happening now, but who is interested in quantum science? If you ask a small kid these days, they are not maybe. But what they are interested in is playing games using the computer. Okay, then they are interested, playing games is also, they are interested in mobiles, buying mobiles, making transactions, getting some objects from the market, delivery fees and so on and so forth. So all of this requires the internet, it requires some technology and so on and so forth. Artificial intelligence is very important, but I will not come into that. But the most important thing which is required is security of this transaction. So that even a child is able to understand why security is most important. And by the way, on the other side, this subject that is applying quantum mechanics to many different areas of not pure science, but say social science and other streams, like even commerce and finance, this is also started. I mean, these are textbooks which have been published. So it is not as if quantum mechanics is confined in the laboratories of physicists and maybe some chemists and so on and so forth, but even other people are applying these laws. But the main focus in the last few minutes is on security of this talk. So what is security? What is the secure way of communicating something? So this is called cryptography. By the way, cryptography is an old subject. Even in classical theory we have cryptography. So you want to communicate with your friend who is far away, but you want to hide this information from some evil person or eavesdropper, right? So use cryptography all the time. For example, even if the Gmail account or other accounts you use are sort of coded. You do not want your friend to know what you are writing to somebody else, right? So this is a way, it is a cryptography. And you set a password for that, your account, and password is what? It is a combination of keys on the laptop, right, or on the mobile, that is numbers and things like that. But in any given keyboard you have a finite number of keys, right? So as sophisticated a password that you can make only using finite strings which are present in your keyboard. Now suppose somebody has a very powerful computer, then he or she can run all possible combinations of all keys. So in principle this is hackable, right? I'm saying from the basic, I mean, very foolish hacker like me can also hack if I have a powerful computer, and smart hackers can hack everything, right? But so the point is that this information that you code using the password that you write, using your classical notions of information is not secure, right? So we have to take a step forward. So now if you go to quantum mechanics, then you see that privacy or security is founded on principles of fundamental physics. So what is principle of fundamental physics? In a nutshell, this is zero superposition, but at the most basic level is the quantum uncertainty principle. That is, if any hacker comes and tries to hack, that is, hacker wants to obtain some information, hacker has to perform a quantum measurement on a given system, and in this process the state of the system will be disturbed, and so therefore the two parties who are sharing this information will know that there is a hacker who is present. Okay, so this is the basic principle, and it can run in many sophisticated ways, but quantum privacy is most fundamental. In principle it is completely secure, and it lies on the it depends on the principles of fundamental physics, but not on something which requires a difficult computation. Classical security relies on the concept of difficult computation. The more and more large passwords that you make, okay, more and more different characters you make, it is difficult to crack, but still in principle it is crackable. Whereas in quantum theory, gathering an information about a quantum state unavoidably disturbs the state. So that is why quantum communication has become so important these days. Okay, and so therefore, so this actually subject is not realized as today, but again 20 years ago. So I mean, quantum cryptography was first discovered, actually implemented, I should say, in Switzerland. And these are the two major players, Bennett and Brassard. So Charles Bennett, of course, is the father of quantum information theory, and he's also visited Calcutta. He's come to S.N. Bose Center in 2018. We were having the 125th anniversary of S.N. Bose. So he came here and stayed. But this happened many years ago. In 1984, these two people proposed the first code for quantum key distribution, and since then it has been actually implemented, and these days you can even purchase quantum QKD machines. Okay, and even in India there is a company in Madras, I forget the name of the company, which actually sells such quantum cryptography. Okay, so now the question is that at a basic level you have quantum cryptography, but the challenge now is actually making things more and more secure, because as soon as you have quantum principles, there are other smart players who can actually even hack the machine. For example, if you buy a quantum cryptographic machine from Switzerland and it comes to you by some shipment, and in the process somebody can use and hack it, okay, even hack the machine, then what will you do? Or even the manufacturer, sometimes you cannot trust. The manufacturer can give you a certain machine which is hackable. By the way, such QKD machines are also used in as voting in Swiss general elections. So in India these days, if you open the newspaper or Google, you will find so many companies. The party will say, oh, somebody hacked the machine, somebody, this because the electronic voting machines you have. But if you apply proper QKD machines, then nobody can hack it. So this is based on principles of quantum. But still some person can hack it. Who is that person? That person is the manufacturer. The manufacturer of the machine can actually send a biased message. So what can you do in those circumstances? So in the last 1 or 2 minutes, I will again tell you something some very recent which is happening these days. This is also an area of research where we are also engaged in. So this is called something which is called self-testing, quantum security through self-testing, and this is verification of quantum states and measurements without direct access to the quantum system. So even if we do not have direct access to the states or quantum devices, some manufacturer has made it, we can still verify whether it is secure or not. And so what we have to do, we have to certify that quantum entanglement is there, and we do not need to trust any manufacturer or any quantum device to do it. Okay, so that is the idea of self-testing. So in a nutshell, so these are two systems, spatially separated systems, to prepare an entangled state, and then if you are the self-tester, if you want to really know, verify that whether these two parties can be trusted or not, whether they have really made the thing, cryptographic machine or entangled state that you require, then what you will do, you will ask some questions from both A and B, you will gather the results and make a mathematical probability distribution, and then you can certify. And by the way, this idea of ours was not only a theoretical idea, it is also been implemented in collaboration with a Chinese group in 2020, 2-3 years ago, and this relies on just very simple quantum optical setup, linear quantum optics, basically through lasers and some detectors and interferometers, so on and so forth. And so you can actually, we have actually been able to demonstrate this quantum self-testing. And finally, we have also been able to demonstrate another way of checking security, that is in a reliable way, even without entanglement, that is just one-sided communication. Okay. So that is just an advertisement, just to tell young fellows that research is very active in this area and in the whole world, and we are also a part of it. Right. So now let me come to the end of this talk. So quantum information science is a very sort of hot area and a very productive area as well in current times. So but there are many key questions that one has to ask. So this is a very nice time, right age for young people to get into this subject. Why? Because both from the point of view of basic physics as well as application. See, I am a basic physicist. Okay, so I come from that background. I became interested in it, and nowadays more and more people are coming into this field who want to do some applications. That is very good, very nice. But even from the point of view of basic science, there are a lot of important questions which remain unanswered, and ultimately they will have bearing on technology. So that is, if you have multipartite systems, more than 2 or 3 particles, how do you, for example, quantify entanglement? So next step is what I said, that how do you detect entanglement experimentally? At a basic level I have shown you through witnesses, operators, but if the entanglement involves more and more complex systems, how to do it? Okay. So then there are many fundamental problems related to it. As I told you from the first slide onward, the whole birth of this subject was motivated by fundamental physics questions. It wasn't motivated by some technology desire, it was motivated from fundamental physics questions, and still such questions, some questions remain, many of the questions remain. For example, like quantum measurement theory, what actually happens, the nature of quantum non-locality. It doesn't violate relativity, but still what is meant by quantum non-locality and what are its consequences. Okay. And this is a very important area. So as I was talking about entanglement, so if two particles move far away, they know they are no longer isolated. They have the rest of the world to interact with. Okay. So the environment comes into play, and the environment, what does it do? It destroys entanglement very soon. Okay. Because a single particle is interacting with many things, say air molecules, so on and so forth, radiation, so on. So in order to achieve, practically achieve these tasks, what I told you, you have to have a measure of control of environment and the decoherence it induces. And what is the biggest hurdle for realizing quantum computers? That is nothing but this decoherence. So that is the biggest challenge. So one has to devise clever means of handling it. The other is called quantum error correction. So this is also an important area. And finally, I conclude with this slide again as an advertisement to young people that many interesting things are happening these days in this area. So there are many different types of challenges and algorithms and physical principles, computations, hardware, and also what are the implications of these ideas for physics. So thank you very much for your attention. So there are questions I'll be happy.
So students, if you are having any question, you can ask.
Thank you for the wonderful talk, sir. So I'm just curious about a very fundamental thing. When you said if I have to write a entangled state mathematically, you said that I cannot write it as a direct product of two states, say 0 or 1. If I cannot write it, then it's an entangled state, right? If I yeah. So and then in the next slide you have expressed it like some 0 cross 1 minus some linear combination of that.
Yes.
Was that an entangled state?
Of course, because it is not a direct product. It is not a direct product. No? There is another term.
There's another
Yeah,
term,
so
some plus or minus something.
So there are two basis vectors 0 and 1.
Yes.
If you write 0 cross 1 or 1 cross 0,
Yes.
then it is a direct product.
Yes.
But when you make a combination it is no
Combination
longer
of
a
that.
direct.
That's right.
Yes.
So, sir, usually what we know very little though, that if there is a coherent beam or incoherent beam of electrons, say there is a coherent beam of electrons of two states, usually I can write it as some normalization constant plus some psi 1 plus some psi 2, then it's a coherent state. And that's why we can apply the principles of linear superposition. And if it's an incoherent beam, I can write it as a direct product but not as a linear combination. So does this coherence play a role for entanglement? That is what I wanted to know, because I don't know anything about entanglement.
Yeah. You see, coherence is something you can even talk about at the level of single particles or single entities. Okay, even in a single electron state, you can talk of coherence of that state. Okay, but whenever you have to go to multiple parties, then entanglement comes in. But what is responsible for entanglement? So if there is no coherence, coherence means that there is some possibility of superposition.
Yes.
That is, as you said, if you want to
Yes.
write psi 1 plus psi 2, if there is a possibility of superposition, then there is coherence. Now, if you want to construct entanglement of two or more entities, if there is no possibility of superposition, then you cannot have entanglement. So you see the two basis vectors 1 and 2, if there is no possibility of superposition between 1 and 2,
Then there will
then
be no
there can be no
so
entanglement.
coherence is definitely
Exactly.
a
So,
criteria.
yeah, coherence or superposition at a fundamental level called superposition, it is a criteria for entanglement. So that is how it is.
Thanks.
considered.
Good afternoon, sir. My name is Kavi. It was wonderful to listen to you and learn about the advancements that are going on right now. So, I have a question, which is that usually we use spins for qubits, right? But can we exploit, say, two different physical properties of a system simultaneously, so that we can do two different computations simultaneously, and thus, giving birth to parallel computation as such?
Okay, let me answer you by coming to this slide, which did not is gone from here or something. Yeah. Yeah, so the next, yeah, this one which I didn't pay much time to, attention to, okay. So, slide, right. So now you consider, okay. So you consider, say, you forget about photons, you consider that some single electron is entering. A single electron has what property? It has spin. Spin is one property. So along a given axis, a z direction, it can have spin up or spin down. Now just imagine this electron falls on a beam splitter. So what is a beam splitter? Beam splitters will split the beam. So for example, if a single electron comes, it can either be reflected towards the upper direction or be transmitted along this line. So now when somebody is here, that person does not know whether a single electron is reflected or transmitted. So now the electron, apart from its spin, has another property which is called the path or linear momentum. So now you can actually use both of this, that is the spin as well as the path, and you can perform some tasks. And how can you do it? You can actually construct an entangle state. So I am telling that entangle state has to be made of two particles. But it can be made of two entities also. That is, a single particle can also be entangled with itself if it has two different kinds of properties. In this case, after the electron passes through the splitter, it has two different kinds of dichotomic properties. One is the spin, which can do directions up or down. Other is the path, which path or down. A single electron can be entangled itself, and you can actually exploit the entanglement. It is not very straightforward. You have to convert that entanglement to something else, but it is possible to use it for information. That is in this one.
Thank you, sir.
Good afternoon, sir. My name is Shora. So, sir, you talked about that we are physically able to realize photon entanglement, and we have also observed that photons can be teleported. But there is something also like fermion entanglement, and research is also going on that area. So, I wanted to know what is the fundamental difference between the two types of entanglement.
Yeah, so there is no fundamental difference. Fermion.
I mean, in terms of the practicality in achieving this.
Because electrons are fermion, so electron entanglement has also been achieved. Neutrons are fermion. Neutron entanglement has been achieved. And even some atoms can be bosons of fermion. So the entanglement of everything has been achieved. Now, as far as practical difficulties arise, you see that fermions, many of the fermions are charged particles. So if you want to, first of all, you have to entangle two charged particles, and then you have to move them far away to use such entanglement. Now, as soon as you move them far away, your environment, as I was just talking about, also has many different kinds of particles. So it is easy for such particles to interact with these so-called fermions that we are talking about, and then the entanglement gets wiped or decoherent. So practically it becomes difficult to handle. In principle there is no problem, but practically it becomes difficult to handle. So this is one answer. But the other question, I don't know whether you asked that question or not, but since you mentioned this fermion entanglement, there is also the issue of entanglement for a collection of fermions, say in a certain ground. For example, you can talk of things like superfluidity or superconductivity, Bose-Einstein condensation, etc. Or if you have a dense collection of high energy particles, and they can be entangled as well, right? So they can be entangled through two means. First of all, one is the exchange interaction, the Pauli exclusion filtration. And for bosons also you have to write the symmetric wave function or anti-conduction. So that is one kind of entanglement. And the other kind of entanglement which I have just mentioned. So at a theoretical level, it is interesting to see how these two entanglements are different. Okay, what can you actually understand about it? But practically speaking, you can only exploit entanglement of two particles for performing such tasks when they move higher. So in that respect, photons are the best.
So sir, is it because of the properties that photons have, because of which we were able to realize it in practical?
Yeah, sure. Because photons, of course, travel with the speed of light. Okay.
Yes, chargeless as well as massless.
Chargeless as well as massless. So it is on the one hand, but the other difficulty is to actually store the state of it. So it is difficult. there are many issues there. But still, so far, what has been achieved in the communication side is mainly through photons, and what is achieved in the computation side is somewhat through photons, but mostly through cold data.
Thank you.
Thank you, sir. My name is Shobhit Ghosh. First thing that I have, I don't know it's a question of physics or not, that you were talking about hacking. Even many calculations are done faster in that quantum computer that you just said. But the calculations of predicting the passwords to hack into some penetration testing. But there are many layers that certain number of combinations or certain trials are given. After that, that data is destroyed automatically. So how will the quantum computers work in that case?
So what you are talking of again is your classical logic, how things happen in the classical world. So there are theories of hacking, there is hackathons, so on and so forth, all of you know. So that is something separate. So quantum mechanics provides secrecy or security in principle. Okay. But now when you have to actually put this into practice, of course at some stage again you will have to deal with these mechanisms that we are talking about. So all that is there, but at least from the fundamental point of view, there is indeed secrecy. But again, as you said, even in quantum cryptography, there are many theories of hacking or eavesdropping, it is called. Okay. So say for example a quantum cryptographic protocol. There are thousands and thousands of works and papers and different protocols. I just showed you one protocol, BB84, which was the first protocol. But after that, there have been many protocols. Then some protocols are easy to crack to a certain extent. Okay, some are more difficult. So what we're talking of is really the details of this subject. If you are interested in, you can go into. But as far as today's talk, so I have to give at least 2 or 3 more talks to come to describe you the well-known protocols, how they can be hacked, what is the level of secrecy. There is something called the secure key rate. Even if there is a lot of hacking, it goes on. There is something which is called the secure key rate, which is still there, something at the core. So all those things are there. So, but today I just wanted to motivate this subject that using laws of quantum mechanics, there is some in principle security which can be found.
Sir, I know this class, I mean normal hacking, the basic hacking I have just little knowledge. I wanted to know that the way that normal computers, classical computers are designed, is this technology we can, I mean using this quantum computing thing that I don't understand properly, they can hack the classical computers as well then?
Quantum algorithm using parallel processing, it's something, if you take say 1 hour to hack using a classical computer, you can, if you run a quantum algorithm, you can hack in 1 minute.
So there will be a power issue, like a heating issue will be there
Of course,
in the transistors.
of course, everything is there. So that is why I said quantum computers are still some way off. I mean, the main issue is to do with power, and it ultimately decoherence, error correction, things like that, of course, are there. So that is why it is still some way off to realize quantum computing. Okay, so Google and other people are claiming they've achieved 100 qubit, 150 qubit quantum computer, but for that stage to come when they will be available in the market may take still some time. At least I don't see it happening in my lifetime. Maybe in your lifetime it will happen for sure. But it is still a fascinating area. People are doing a lot of work. But quantum information, some people get confused, is not solely to do with quantum computing, as your dean was also. There are many, even if you are interested purely from an application point of view, forget about the basic science, even then this area of quantum communication or quantum, another thing is quantum metrology or quantum physics. It has already come, and it is surely going to come in a very, very big way, because no communication, no transaction will be secure in future. You see, so at some stage your quantum cryptography, quantum secret sharing protocols have to come into picture. So that is why there is a lot of work going on, both theoretical as well as practical.
It's a last question that he just asked, that when we will consider some collection of particles, then each particle and their respective entangled counterpart will be in somewhere else. Then
Yes.
for the total system,
No, not that way. So if I have two particles, one is A is entangled with C. I have three particles. A can be entangled with B, B can be with C, and C can be with A. So it is tripartite entangle. So on and so forth, four particles. But even there is a classification. Suppose we make a cut somewhere. We make one cut. Is the system still entangled? So it is a complicated system. So there is no one counterpart somewhere. It is multipartite. It is only called genuine multipartite if each of the subsystems is entangled with every other. But it is not a genuine entanglement if you make a cut and then it goes. Okay, so there is a classification. So it is a very rich and fascinating thing.
yes, thank you, sir.
Good afternoon, sir. Sir, I was just curious to know that can quantum teleportation be used to probe gravitational physics? If yes, then how?
No, so far that I know, I cannot think of gravitational physics, because you mean that to explore something which is very far away. Yeah, but you see, first of all, you have to put your friend at that distance. Otherwise, who will do the protocol? So teleportation, somebody has to communicate with somebody else. The friend there has to do something. Okay, even in satellites, they put some machines or robots who can carry out the protocol. But if you think of gravitational physics, that is say far, far away in a galaxy.
Yes, sir.
So first of all, you have to put some friend there, or some other say extraterrestrials have to be there. So you have to establish some connection with extraterrestrials. Then you can do. But by normal ways, I don't see that, at least at present, how gravitational physics can be probed with quantum.
Thank you, sir.
So I think no more questions. It was a lovely interaction session. So now I would request our Dean Research and Development, Professor Momita De, who is also a senior professor of our department, Momita Mukherjee, to give a vote of thanks. Thank you, Professor Majumdar, for this excellent talk. We are really we are grateful that you have accepted our invitation and given such a wonderful talk, and we get immense information from your lecture today. So, and the interaction, as you have already seen, students have really enjoyed the talk. That is very much reflected from their interaction. So thank you very much, and from Department of Physics, I am thankful to our head of the department for arranging such a nice program. Thank you, thank you.
Thank you, ma'am. So with that, we come to the end of the today's program.